Hello students, welcome to my channel Arun's Physics Portal. In this lecture, I will be talking about Thevenin's theorem. This topic is important for BSc students of Physics and Electronics and also for BE and BTech students of EEE and ECE branches. The NET and JRF aspirants will also find this topic useful. The complete note of this topic is provided here for your convenience. I hope you enjoy going through it. Now let us come to the topic. Thevenin's theorem. This theorem gives a way of simplifying multiple loop electrical circuits. We consider here, for example, the circuit shown in figure 1. It has 4 different loops. This is the first loop, this is second loop, this is the third loop, and this is the fourth loop. And RL is the load resistance here. If we have to find out the current flowing through RL, then we have to solve 4 loop equations. Each time we change the value of RL. RL के डिफरेंट वैल्यू के लिए हमें यदि करंट निकालना हो थ्रू RL तो हमें हर बार 4 डिफरेंट लूप इक्वेशंस को सॉल्व करना होगा. This process is tedious and time consuming. Thevenin analyzed such circuits and was able to show that the entire circuit to the left of the point A and B can be replaced by a single voltage source known as Thevenin's voltage source and a single resistance known as Thevenin's resistance. The solution of the circuit shown in figure 1 is shown here in figure 2. So here the Thevenin voltage is 4.5 volt and the Thevenin resistance is 1.5k. So the entire circuit shown in figure 1 can be replaced by the circuit shown in figure 2. As shown or as it is clear from the figure, this figure 2 is much simpler than the circuit shown in figure 1. Now let us see the statement of Thevenin's theorem. What is the statement? Any two-terminal linear network containing linear impedances and generators connected to terminals A and B can be replaced by an equivalent circuit consisting of a voltage source ETH in series with an impedance RTH. So what is Thevenin's voltage source ETH? ETH is the voltage across the load terminals when the load is disconnected. If you consider the circuit shown in figure 1, then ETH is the voltage between the points A and B when the load RL is disconnected here. Okay, everything else remains the same, but we have disconnected the load resistance. So the voltage between the points A and B is the Thevenin's voltage. Okay, and what is RTH? RTH is the resistance across the load terminals when all the voltage sources are replaced by their internal impedances. So as shown here, we have replaced the voltage source that appeared in figure 1. Everything else remains the same. So RTH is the resistance between the points A and B when the voltage sources are removed. Okay, now let us see how to prove this theorem. To prove this theorem, we consider the circuit shown in figure 3. We have 2 different loops here. E is the voltage source, R is the load resistance, R1, R2 and R3 are 3 resistances in the circuit. The circuit shown in this figure had 2 different loops. This is the mesh 1 and this is mesh 2. The current in mesh 1 is IA and the current in mesh 2 is denoted by IP. We call this current IA because this is the loop in which we have a voltage source. So this loop is active loop. This mesh is active loop. So we denote the current as IA. In the mesh 2, we have no voltage source. So we represent the current in this loop by IP, meaning that this is the current in the passive loop. Now let us write the Kirchhoff's voltage law for the two loops shown in figure 3. We have taken the currents to be positive when flowing in the clockwise direction. So IA flowing through R3 is positive, okay, whereas the current IP flowing through R3 is negative for mesh 1. Similarly, for mesh 2, current IP is positive. So current IP through R3 is positive, whereas the current IA through R3 is negative. Now let us write the two mesh equations for mesh 1 and mesh 2. For the mesh 1, we have two resistors there, R1, R2 in series, and the current is IA. So this is R1 plus R3 into IA. Then again minus R3 into IP, because this current is opposite to the current IA. And this is equal to E, the voltage applied in the mesh 1. So this is the equation for voltage law applied to mesh 1. This is our equation 1. For the mesh 2, we have R2 plus RL plus R3 into IP, okay, minus IA into R3 is equal to 0 because there is no voltage source here. Now we have to find the value of IP, the current flowing in the mesh 2. How to solve it? The equation 1 and 2. To solve this equation, we use Cramer's rule. Now let us find the value of IP using Cramer's rule explained here. Refer to equation 1 and 2. IP is the coefficient of B1 and B2 here. So Y stands for IP in equation 1 and 2. So how to find the value of Y? You use this equation. So IP is, in the numerator we have A1, A2. So A1 in equation 1 is R1 plus R3. In equation 2, A2 is minus R3. C1 is E and C2 is 0. Okay, so this is your numerator determinant. In the denominator, we have A1, B1, A2, B2. So write the value of A1 and B1 from equation 1 and A2 and B2 from equation 2. Now solve this determinant. Okay, if you solve it, the value of IP comes out to be R3 upon R1 plus R3 into E upon RL plus R2 plus R1 R3 upon R1 plus R3. As we will show you later, this value is nothing but your Thevenin's resistance RTH. So equation 3 gives you the value of load current. Now we have to find the value of Thevenin's voltage ETH between the terminals A and B of the network. How to find it? To find the value of ETH, we disconnect the load resistance RL from this part connected between A and B terminals. So when this is disconnected, there is no current flow through resistance R2. So whatever is the potential at A dash is potential at the point A, and therefore EAB is also equal to EA dash B, and this is your Thevenin's voltage. So what will be the voltage here? This is the voltage across R3, and the voltage across R3 is nothing but the current IA into R3. Okay, so what is the value of IA? IA is E upon R1 plus R3. This is the current that flows in this mesh. Okay, so ETH is equal to EAB equal to EA dash B, and this is nothing but IA into R3. The value of IA is E upon R1 plus R3. E upon R1 plus R3 into R3. So this R3 is here. So this is the value of ETH. This we have shown here. Okay. Next comes the value of Thevenin's resistance. Thevenin's resistance is obtained by disconnecting the load resistance between the terminals A and B and replacing the voltage sources in the circuit by their internal impedance, if any. So we have replaced the voltage source from here. Okay. So if you replace the voltage source from this part, R1 and R3 come in parallel. Okay. So when they come in parallel, and if I assume that the resistance between A dash and B is Z, then Z will be R1 R3 upon R1 plus R3. So the Thevenin's resistance between the terminals A and B is simply the resistance R2 plus resistance of this part. This is R2 plus Z, and if you put the value of Z here, this is RTH is R2 plus R1 R3 upon R1 plus R3. Clear? So from equation 3 to 5, it follows that the current IP is ETH upon RL plus RTH. This is your RTH as we have mentioned earlier, and this is the value of the current. Okay. So the circuit shown in figure 3 by using Thevenin's theorem can be replaced by the circuit shown in figure 4. So this is ETH here, this is RTH, this is RL here between terminals A and B. So the circuit shown in figure 4 is equivalent to the circuit shown in figure 3, and this proves the theorem. Clear? Now let us see an example. Find the Thevenin's voltage and Thevenin's resistance for the network shown in figure 5. So this is your figure 5. This is one loop, this is another one, and this is the terminal A and B across which the load resistance can be connected. You see here that across the 10 ohm resistance we have a voltage source of 2 volt. So across the 10 ohm resistance the voltage will be 2 volt always, because this is a DC source. So if I assume that the current in the mesh 1 is I, then application of Kirchhoff's law to this mesh gives you how many resistances are there? 2 ohm, 8 ohm and 6 ohm. So this is 2I plus 8I plus 6I, and the total voltage is 4 volt minus 2 volt. Why minus? Because these two voltage sources oppose each other. So this is 4 volt minus 2 volt is 2 volt, and you finally get 16 ohm is the total resistance in this mesh. So 16 ohm into I is 2 volt, or the current I is 2 volt upon 16 ohm, and this is equal to 1 upon 8 ampere. The Thevenin's voltage ETH between the terminals A and B can be found as follows. How to find the Thevenin's voltage? We disconnect the load resistance from the output. So ETH is the voltage between the points A and B. And since the circuit is open, there is no current flow through the 3 ohm resistance. So voltage at the point A is the same as voltage at the point this. Okay. So Thevenin's voltage between A and B is simply equal to the voltage between the point A dash and B. Okay. So voltage between the point A dash and B is simply 6 ohm into I. This is the voltage drop here plus 2 volt. Okay. So this is 6 ohm into I plus 2 volt. So this comes out to be 2.75 volt. because I is equal to how much? I we have already calculated. This is 1 upon 8 ohm, 8 ampere. So this 6 into 1 by 8 ampere. This is 3 by 4 volt plus 2 volt, and this is 2.75 volt. Now we calculate the Thevenin's resistance of the circuit. To do this, we replace all the voltage sources by their internal impedances. So we have removed the voltage source of 4 volt from this part and 2 volt from this portion. If you replace 2 volt source from here, then this resistance is now short circuited because both the current will flow through this part only and no current will flow via 10 ohm resistance. So this is now short circuited. So whether this is placed here or we remove here, it makes no difference. So the simplified form of this figure is here. We have 8 ohm and 2 ohm in series and 6 ohm is in parallel. With this one, we have 3 ohm in series. So 8 ohm plus 2 ohm in series is equal to 10 ohm here plus 6 ohm in parallel with 10 ohm resistor. So if it has the value Z, then the impedance of this part is can be found by using this formula. 1 upon Z is 1 upon 10 plus 1 upon 6, and this gives you the value of Z as 3.75 ohm. So this is 3.75 ohm plus 3 ohm. So the resistance between the point A and B is simply 3 ohm plus 3.75 ohm, and this is 6.75 ohm. So the Thevenin's equivalent of the network shown in figure 5 is shown here in figure 7. Thevenin voltage is 2.75 volt and Thevenin resistance is 6.75 ohm. I assume that you like this presentation. यदि आपको मेरा यह प्रेजेंटेशन अच्छा लगा हो तो इसे लाइक करें, शेयर करें और मेरे चैनल को सब्सक्राइब करें. Thank you for watching. See you next time with some other topic of interest. Till then, goodbye.